Hey guys, this video is going to be the onboarding for all the knowledge and concepts you need to know in order for you to contribute meaningfully towards our club's first project. To remind you, our project is going to be controlling a video game character's movement with our thoughts. How exactly we're going to do that is by using a type of brain-computer interface called a motor imagery BCI that can label and classify the type of motor action that we're thinking of. And more specifically towards our project, we're going to keep it simple as it can be and classify whether we're thinking of our right hand or left hand. The task is pretty ambitious. I try to make it easier to understand during the interest meeting, but I think I might have done the opposite. Like when I was introducing what the project, how the project was going to be done, I basically said, all right, guys, it's going to be hard, but I'm going to make it harder for you. With this presentation, I hope to break down the ideas, concepts down into intuition. All right, let's get started. The steps we need to take to go from thinking about an action to controlling a video game character is through first getting the signal, which is the signal acquisition part, and then as we'll learn, it's not as easy as we think. So we need to do some processing of that signal to get purely the brain wave, and then using that brain wave to label it as left or right hand. But before we can get the signal, I'd like to give you the basic knowledge on where this brainwave comes from and how the brain works, and also the nature of EEGs in general. The brain has many different regions, and each region has their own function. The region that we care about is called the sensory motor cortex, and it runs horizontally on the midplane of our brain. The sensory motor cortex function is with motor intent and also motor action, and its corresponding brain waves that come with it are the beta waves and the alpha waves. Within our project, we want to get these signals purely and then use them to train our machine learning model. But getting the pure brainwave is actually very difficult because our reading that we get from our EEG data is not made of pure brainwaves. If it was like that, we probably wouldn't need this slide. Our task then is to isolate just the pure brainwave data from our EEG data. And I hope to illustrate that image with this image. There are two waves which represent two different sources, and if you add those waves together, you get the resultant wave. And this is how nature really works. You can imagine our wave 1 as our raw brainwave data over here, either our alpha or beta waves, and then our wave 2 is like some electrical noise that we don't really want. And then if you add those two together, you get a resultant wave, which is our raw EEG data. This is what we get, but we actually want just pure brainwave data. So the task for us is to isolate raw EEG data and remove the stuff that we don't want. We get as close as possible to the actual brainwaves that we make when we're thinking. Oh, how exactly are we gonna do that? There's equipment that we have, and it can do both of that. It can get the signal, it can get the raw EEG signal, it can filter the stuff that we don't want, and then it can also isolate the pure things that your brain waves. There will be electrodes that will be attached to our forehead in order to acquire the signals from our brain. That's an interesting choice because, as you remember, I just said sensory motor cortex is where the brainwave beta and alpha come from, but then we have an electrode on our forehead. Yeah, so nobody wants to go bald, and and there have been literature supporting the idea of using electrodes on the forehead in order to get alpha and beta waves or motor imagery, and I'm glad that's possible. So for convenience, we're gonna try to get motor imagery from our forehead. If that doesn't work, someone might go bald. And then the signals going from the electrode through a chip, which we call the pill, and it does the canceling of the signals that we don't want, and also amplifies the weak signal, the weak brain wave signal that we actually want. We feed that into the computer using Arduino, and and then from there, we're gonna do some more processing. The chip that we're using does a good job of filtering the electrical noise within our environment, but it neglects physiological noise from our body. Since we're using forehead electrodes, we also have noise coming from our eyes whenever we move, because the eye is a pretty big source. When you move it, it also puts a reading onto the EEG, but we cannot use that because that's not EEG. We don't want that, and that's where signal processing comes in. After we got the pure brain data, we want to know how strong certain frequencies are within that data. And remember, we want alpha and beta waves, which are in the frequency ranges of 8 to 12 hertz, 12 to 30 hertz. And the fast Fourier transform will tell us how strong certain frequencies are within the data. Ideally, we want alpha and beta frequency ranges. And after we get the strength of the signals of the alpha and beta waves, we can compare what the difference is between a left hand and right hand motor imagery is from the frequency domain, and then train a machine learning model on it, tell it to label either or, and then we move a game character after that. And to summarize, in order for us to control a video game character with just our thoughts, we have a signal acquisition device that filters and also amplifies our EEG signal. And then we need more processing to remove physiological artifacts like our eye. And then we're going to use the FFT to get the strength of our frequencies. Then use a machine learning model to train it on data that separates whether we're thinking of our left or our right hand.